So let me start by saying, of course, we were talking about boundary conditions last time, and we looked briefly at this equation. This example, I think a simple thing to do would be to, or a useful thing for me to do would just be to remind you of something that you already know, namely how to solve this kind of a system. So let's suppose that we have the conditions, what did I call them? Alpha, say, let me get them straight so I don't do things. All right, alpha sine Ka plus beta cosine Ka, that's equal to some constant C, and alpha sine K minus A. Well, here, let me fix that. Plus beta cosine K minus A equals, let us say, D. Then, you know, obviously, you learned in high school how to solve such a system of equations. This second equation is minus alpha sine Ka plus beta cosine Ka, and this is equal to D. And so you say beta, oh, damn it. This, oh Lord. The screen, all these touch. All right, so I'm back to where I wanted it. So what you do, of course, is you say beta cosine Ka is D plus alpha sine Ka. And then you substitute that into the first equation, and that gives you 2 alpha sine Ka plus D is equal to C. And so your solution is alpha is C minus D over 2 sine Ka. And then your equation for beta is that beta is equal to D plus alpha sine Ka, which is C minus D over 2. It's that divided by cosine Ka. And this then is C plus D over, oh God. Over 2 cosine Ka. So what we've got then is we start with two differential, two boundary conditions, and we're dealing with the differential equation minus, hold on, let me fix this. It's minus y double prime is equal to k squared y. And of course, you know the two solutions are sine Ka, cosine Ka. And then you impose these boundary conditions at the top. Let me switch to a different color here. Lord. Green, say. Then you impose these boundary conditions, and you get that alpha is equal to this and beta is equal to that. And so what does this tell you? This tells you that if you set the boundary conditions at, these boundary conditions are at x equal to a. Look at that, damn it. These boundary conditions are at x equal to plus or minus a. Then you can solve them, and you get a unique solution, alpha given by the difference of the two boundary conditions divided by twice the sine, and beta, the sum of the two divided by twice the cosine. And so this is an example of how the boundary conditions, how for a second order differential equation, two boundary conditions give you a unique solution. And no matter what C and D are, we always have a solution. And so the solution is y of x is equal to C minus D over twice the sine Ka times, now let me make sure, which did I call which? Right. Right. Sine. So this is sine kx plus c plus d over 2 cosine ka cosine kx. So these satisfy the appropriate boundary conditions at minus at k equal to, at x equal to, whoops, this is stupid, I screwed up. Hold on, let me fix this. Oh, that one was right, actually. So if we said x equal to a, then the first term is c minus d over 2. The second term is c plus d over 2, and we get y is equal to c, and so forth. Okay, well, this is all stuff you know, but this is just an example to illustrate what it is that one is talking about here. The next topic is something that I may have added to the book, but it's a useful example that you should know about, something you learn about in quantum mechanics class. But you know, as usual in quantum, in a physics course, we skip over the math as much as possible. It was introduced in 1924 by a mathematical physicist named Jeffreys. From the name, I would gather he was English. And it's a way to find approximate solutions to second order differential equations. So it's that general. What he was saying was, well, if we write y equal to e to the z, then we know that z is really the important thing. And we can form the derivatives very easily because they're derivatives of an exponential function. And so now we have an equation that's nonlinear in z. On the other hand, we can imagine that, or we can pray that z varies sufficiently slowly that the second derivative is negligible. So we drop the second derivative and get a reduced equation, and we call its solution z0. And all that's left here, of course, is z0 prime. And so we have a quadratic equation for z0 prime and in terms of p and q, and so we can solve it. Once we have z0 prime, we can differentiate it once, and we then get a more exact equation for a more exact solution. We seek a more exact solution, namely we stick in our very approximate or crude value of z0 double prime or of z1 double prime, approximating it as simply the derivative of z0 prime. And so then we we have this equation, and then we can solve this differential equation for Z1 prime and integrate it. Z1 prime, then the equation for Z1 prime is quadratic in Z1 prime, and it involves not only P and Q, but also our approximation for Z0, or for Z0 double prime in particular. And so this is a general first approximation, so to speak, to a differential equation, and it works. Well, it works when it works. It works sometimes, sometimes it doesn't. And it works when basically the second derivative of Z is suitably small. In other words, when this term is fairly small or slowly varying. So an example is, of course, Schrodinger's equation and the time-independent, one-dimensional, non-relativistic Schrodinger equation. So we said psi equal to e to the w, psi prime is w prime e to the w, psi double prime is w double prime plus w prime squared e to the w. And so we get this, the Schrodinger equation turns into this equation for involving w and v. And what we do is we first drop the w, the second derivative of w. See, this is w double prime. So I've got two w's here, doubles here, and then it's screwing up my lips. So we just find the lowest approximation is w0 prime is just the square root of this thing. We differentiate it and get an approximation for w double prime. And we substitute that into this equation. And we keep a 0 here and put a 1 here, and we solve for the 1. And so we then get directly this equation. So maybe I should fill that in just a little bit. In other words, what we have here is we have an expression for w0 prime. And so our approximation then for w0 double prime is a half 1 over the square root of minus 2m e minus v over h bar squared. And then the derivative of that, which is 2m over h bar squared v prime. And so that's the thing that you see here, basically. And so then our equation our equation is w0 double prime plus w1 prime squared equals that. And so substituting in for this equation, we have, for this expression for w0 double prime, what we have is mv prime, there's not a double prime there, over this square root of minus 2m e minus v over h bar squared. So that's the w0 double prime. Then we have plus w1 prime squared equals minus 2m e minus v over h bar squared. So we solve that for w1 prime, and of course we get this. And then with a considerable amount of massaging, by the way, the I here comes just allows us to switch e minus v to v minus e, or v minus e back to e minus v. Anyway, with some, so this is the exact approximation. You can then approximate our approximation by keeping the first term and then the correction, the best simple approximation to this is this plus that expression. And if one then integrates W prime, in other words, what you have to do is, this is the W prime here, or Z1 prime is an analog of W prime, and you integrate that, and what you get is this, and you get two special cases. When V is greater than E, the thing is a decreasing exponential, and so in particular, that says that if you have a, let us say, a potential that looks like this, and your so let's see, we want to talk about what E is. Well, let's see, I should have made, let me undo that. Let me make this the potential. All right. Now, if we switch to say V, suppose your energy is up here. Well, let me switch to red maybe. Suppose your energy is up here. Then the solution propagates simply as a not as a plane wave, but it's basically a unimodular phase factor that just changes as you move with space. And over here, where E is a great deal bigger than V, then so in let us say this region, E is greater than V, and so this thing oscillates very rapidly, over here less rapidly, and then over here again rapidly, because the speed of oscillation is E minus square root of E minus V. On the other hand, if you have a situation where your energy is actually here, then you oscillate somewhat slowly here, but you don't all right, let me do a better picture here. So let us say this might be an oscillation like this. So then as it enters the region where V is greater than E, it then decreases exponentially and then starts oscillating over here. So it looks like this. So that's basically the picture. The thing leaks out, and this was used to study nuclear physics, and in particular nuclear decay, and in particular alpha decay. In other words, you have a big nucleus and an alpha particle in here, which of course is 2 protons and 2 neutrons. And it's sort of happy in there. It's not very happy at the edge, but it turns out to be even happier outside if the nucleus is unstable. And so what you have is an energy barrier. The energy barrier is here at the edge, and eventually the alpha particle, let us say if I do the, just looking at it as a function of R, so this is R. So the potential is something like this. At the edge, it's like that, and then it goes down to 0. And so the alpha particle is sort of doing this, and then it goes down like that, and then it comes out and oscillates faster. I don't know why I made it bigger. That was stupid there. So let's just say and here it's oscillating faster, but it is a lower absolute value. So this is the chance of this is sort of like what the wave function looks like to describe alpha decay of a nucleus. The alpha particle bounces around happily inside, and then we say tunnels through to the outside. So this is tunneling. Jesus Christ. This is tunneling. And I don't really know how to spell tunneling. Anyway, here's another example. This is basically an example of a second order differential equation, but it's not WKB. Well, maybe it is. Let's just see what it is. So what we do is we're going to neglect the second derivative, and well, no, we're not neglecting it immediately. What we've got is this differential equation. This is the Hubble rate. The Hubble rate is the scale, the time. All right, let me write that down. H is A dot over A, and A is the scale factor. And so first of all, we imagine, for simplicity, that the field is spatially homogeneous, so we get rid of this term. Spatial homogeneity means you have a lower energy solution, so it's not implausible. You then set phi equal to e to the z, and then you get this expression. We're going to assume that the scale factor is not changing so much, so we're going to drop h. And if we drop h, then we've got the equation I do not know how to get rid of that damn thing. We have so we have the equation then z doubled, sorry, z double dot plus z dot squared if we drop h plus c squared m over h bar, whoops, h bar squared equals 0. And so the proceeding actually in the WKB way, we then neglect. So we basically neglect this term, and then we solve for Z1 dot as this expression here. In other words, we get Z0 is equal to IC squared M over H bar. And then minus 3/2 H. So we put, I'm sorry, I should not have tossed in that extra thing. What we get is simply this, which is what I wrote down at first. So then automatically Z0 double prime vanishes. And so now we have this differential equation in this form if we put H back in. And so then we get that Z1 prime is this, just solving this quadratic equation we get. God. Oh. Solving this quadratic equation, we get this solution, which we approximate in this way, where H is A dot over A. And then our axion field is E, let me switch to blue, the axion field then phi, which is e to the z1, is e to an integral of I c squared m over h bar squared minus 3 a dot over a dt. And of course, what we have then is the first term just gives us, at least if we choose the plus sign and a minus sign and add them together and divide by 2, we then get a cosine of the integral of c squared m over h bar. I keep writing h bar squared. That's just sort of silly. dt prime up to, well, m might be a function of time, so we'd keep the integral. I don't know why m would be a function of time though. But anyway, the rest of this is an integral of dA over a. So it's integral dA over a, so it's log a. And that gives us then, and there's a 1/2, which I left out. And so this gives us all of this times a to the 3/2, and then you evaluate that at t1 or t and t1, and actually there's a minus sign, so it's the minus 3/2. Anyway, what you get then is this expression for an axion field. This is from Weinberg's book on cosmology. Let me see if there's any chat questions here. So the next topic is something of theoretical interest, and I think it's good to understand these things, and so I'm going to go through them. Suppose we have an energy functional p u prime squared plus q u squared dx, and so when is E functional, or when is E stationary, or equivalently, when is E maximal or minimal? And so what happens if we do that? Well, we say the variation of E is given by an expression of this form. In other words, we have 2u prime du prime and 2u du. And so we get these expressions here, and du prime is the prime of du, and so substituting in here, we have this expression. We integrate by parts, and we wind up with the energy being stationary if this quantity is 0. And so, so suppose we want to say that that E is stationary with respect to all tiny changes in U that vanish at the endpoints. Well, in that case, what we do is we get that the differential, we get that this term vanishes in any case because du vanishes at the endpoints. And so what we have is simply the requirement that this vanish at every point between A and B. And so we get that U satisfies this differential equation. And this is what's called a self-adjoint, a self-adjoint differential equation, or an equation of self-adjoint form. Let me raise this desk just a little bit. If instead we say that E is the energy is stationary with respect to all tiny changes, including changes in the changes of U at the boundaries, then U has to satisfy not only the differential equation, but also these boundary conditions. Here, these boundary conditions are Neumann boundary conditions, and they're that U prime vanish at the two endpoints. And so what we've been led to is by considering functionals that are quadratic in the derivative, in the first derivative, and don't have any linear terms in the first derivative. What we have is that the function is, the energy is stationary if the function satisfies the differential equation, and we may or may not want it to satisfy the boundary conditions, but the main thing is that it satisfy the well, if we want it to be completely stationary, then it has to satisfy not only the differential equation, but also the boundary conditions. And so this leads us to consider self-adjoint differential operators. You see and of course the stationarity of the energy is the condition that the energy be maximal or minimal. And so to find the maximum energy or the minimal energy of a certain system, we need to have it satisfy a certain equation of this form. And that's what's called the self-adjoint form of the differential equation. You see, it can have a linear term in it, but the linear term has to look like this. And so these, and there's another feature of these differential operators that are formally self-adjoint, formally meaning that the differential operator looks like this. And the one interesting thing about these is that if we let UL operate on a function U and then multiply from the left by V, we have this expression here. And so substituting for L, we have this. Now, if we integrate by parts and massage like this, what we find is that VL of U is L of V times U plus this thing here. And notice this is a Wronskian. And this is what's called Green's formula. So Green's formula for the asymmetry of this matrix VLU, in other words, VLU minus ULV, is that it's the Wronskian evaluated at the endpoints, at B minus the Wronskian value evaluated at A. And its differential form then is that the derivative of this, the derivative of the integral, which is say just VLU minus ULV, is then equal to P times the Wronskian differentiated. And so it's the derivative of the right-hand side, which is the derivative of P times the Wronskian. This turns out to be called Lagrange's identity. So these people were completely on top of all this material. So if we have twice differentiable functions that satisfy the boundary conditions and make the boundary term vanish, then the operator L is symmetric on these functions U and V. So the idea here is that you imagine you have a space of functions U and V, you have a differential operator whose form is self-adjoined, which is to say it looks like that. And then if you have functions such that this Wronskian term vanishes at the endpoints, then what we've got is a a self-adjoint system, or we can say L is a self-adjoint operator on this system, so to speak. The mathematicians are more cautious than we with language. And then what happens is that L, so a formally self-adjoint operator on a system of equations that are suitably differentiable and so forth and satisfy the boundary conditions that the Wronskian vanishes when multiplied by P, then the matrix VLU then is symmetric. VLU is LV on U, or is equivalently VLU. So VLU, and it's also ULV. And since everything's real, this is also LVU. So we're talking everything real here. So what we say is that a real linear operator A that acts in a real vector space and satisfies a relation like this, well, we said that it was for all vectors in the space, we said to be it was symmetric or self-adjoint. And so what we say here is that L is symmetric or self-adjoint on the space of functions that satisfy this boundary condition. In quantum mechanics, of course, we normally talk about things that are complex. And so we let chi equal to, say, psi equal to U plus U1 plus I U2, chi equal to V1 plus I V2. And now if the U's and V's satisfy the boundary conditions that make these boundary terms vanish, then what we have is that we have VJLUI is L VJUI for I equal to 1, 2. And in that case, we can say that the P times the complex Wronskian at B minus that at A is 0. And so we can say that chi L psi is equal to L chi star psi, or L chi psi. And this is the expression that we use to say that L was a Hermitian matrix, or a self-adjoint matrix. And so in chapter 1, we said that a linear operator that satisfies this relation is said to be self-adjoint or Hermitian. And so what we have then is that a formally self-adjoint differential operator on a space of functions that satisfies the boundary conditions like this is then self-adjoint or Hermitian. So this is the mathematical basis of this term Hermitian that we use all the time in quantum classes and in quantum field theory. Or in quantum field theory, and because of all the infinities, we don't know quite what the hell we're doing. So the idea then is a self-adjoint system, and a self-adjoint differential system. You have two boundary conditions that are linear and homogeneous, and you have a domain. The domain is the set of functions that satisfy either the what are called Dirichlet boundary conditions or Neumann boundary conditions. And then you say, well, suppose U satisfies the boundary conditions if the set of all function, or let us say that D is the set of all functions U that satisfy the boundary conditions, then the adjoint domain is the set of twice differentiable functions that make this Wronskian boundary condition vanish for all U's that are in the domain. So the V's are such that if U is in the domain, if U satisfies the boundary conditions, then V makes the thing satisfy the Wronskian boundary conditions. And so then what we say is that a differential system is regular and self-adjoint. And so this is basically the mathematicians covering all bases, so nobody slips. And what they have then is that a differential system is regular and self-adjoint if the differential operator is formally self-adjoint. Well, this is formally self-adjoint. If the interval is finite, if P prime, and Q are continuous real functions of X on the interval. So we're going back to the real domain here. And if P is positive on the interval, and if the two domains can coincide, in other words, if the U's and V's are the same functions. So in other words, the set of functions that satisfy the boundary conditions also make the Wronskian term vanish. Then what the mathematicians have shown is that if you give them all of this, then they'll tell you, well, if D is the set of all twice differentiable functions that satisfy either Dirichlet's or Neumann boundary conditions, and if P is continuous and positive, then D star is the same as D. So that simplifies the assumptions actually. And a real formally self-adjoint differential operator together with the boundary conditions forms then a regular self-adjoint system on the interval with if P is positive and so forth. So what you have then is if you have one of these regular self-adjoint systems, then you can say that VLU is the same thing as ULV, and you have that it's basically a symmetric operator, and or L is self-adjoint. If the domain is complex, then you have chi L psi, which is chi star L psi. You can write it as L chi star psi. And so then what you have is chi L psi is L chi psi. And so this is in effect a Hermitian matrix, and we say it's a self-adjoint, or the differential operator is self-adjoint or Hermitian. And examples of this are sines and cosines. These are this operator is about as simple as you can get for a self-adjoint second order self-adjoint differential operator. It's self-adjoint on the interval. It has P equal to 1, Q equal to 0. You can use if the boundary conditions well, you can take the boundary conditions such that the sine of nx is other solutions, or cosine of nx, depending on your boundary conditions. Legendre's equation is also, it can be written as self-adjoint form like this. The differential equation then, if you is this, and it turns out to be singular because P vanishes at the endpoints, but it still works perfectly fine. Hermite's system looks as a differential operator as this, and it is formally self-adjoint, but now the interval is infinite, so it's not technically a self-adjoint system, but it still works if you choose the domain to be functions that are twice integrable and suitably smooth, go to 0 to infinity suitably quickly. Now, here's the important thing that, or one of the important things, namely that you can take any generic second order real linear differential operator and make it self-adjoint, make it formally self-adjoint. And so the formally self-adjoint form would be this, or if you multiply out the d by dx on P d by dx, what you have is this expression here. And so to change that into self-adjoint, so in other words, if you start with L0 and you want to make it into the same form as L, the first thing you do is you divide out the term that that you don't want to be there. In other words, the term that multiplies d2 dx squared. So you divide by that, and then you get something of the form minus d2 dx squared plus minus h1 over x over h2 d by dx, and then minus h0 over x. So you divide by minus h2. Then you multiply this by this prefactor, which is the integral of h1 over h2, where h1 and h2 are these functions in the original L0. And the lower limit is arbitrary. And because that just means you have an extra, since P is, well, anyway, that's just arbitrary. And so now you have the product PL1 is formally self-adjoint. And so you set L equal to PL1, and so that's if you then do that, well, what was L1? L1 was this thing here with minus sign. So the minus sign comes out. You have this exponential of a ratio, and then you have this structure here, which goes there. And then what you can see is that this that we can rewrite this in this form. Because if we have minus d by dx on this, what does it give you? Well, if the derivative goes, it just hits the derivative, you just generate the first term. But if the derivative, Christ, why are there these stupid features of Zoom? If the derivative acts on the exponential, then it pulls down an h1 over h2 and gives you the second term and only one derivative. So that gives you this term. And then this term is just there automatically. Oh, and you subtract this, and this term gives you that. Sorry, so that's why it's there automatically. And now this is of the self-adjoint form, because this thing here is P, and this whole thing is Q, and so so Q is see, this is P. So Q is minus P H0 over H2. So in other words, we can turn any self-adjoint, we can turn any second order linear differential operator L0, which would say anything like that, we can turn into a into this form, the self-adjoint form, if we multiply it by something we can call rho, which was minus 1 over h2, this exponent of the integral. This thing we call p, so it's equal to this. And the two differential equations have the same solutions under the transformation, but under the transformation, the eigenvalue equation becomes different. It now becomes, you see, now LU is PU prime prime plus QU. This is then not lambda U, but the whole thing got multiplied by rho, so it's lambda rho U. And this thing then is called a Sturm-Liouville problem. This is an awkward name to pronounce because actually it's Sturm-Liouville, because this is German and that's French. It's often true in physics that H2 is negative, and which is why this minus sign is particularly appropriate. The weight function is often typically positive if H2 is negative. So let's see, maybe I should put in a few more steps here. What we've got here is we start out with an equation. So let me switch colors. We start out with an equation. I don't know what the hell this thing is. how do I get rid of it? Well, I don't know. Anyway, what we start out with is an L0, which is H2 D2 dx squared plus H1 d dx plus H0. And what we do is we first say that L1 is just equal to minus oh Christ, minus 1 over H2 times L0. And so once we've done that, what we have is minus D2 dx squared minus H1 over H2 d dx minus H0 over H2. So that's what we have there. And then we say L is rho L1. And that is then rho or minus rho times D2 dx squared minus H1 over H2 d dx minus H0 over H2. So this is our expression here where rho isn't arbitrary. Rho is well, effectively, what was rho? Actually, this is simpler than I'm making it. You see, this rho is just simply it's the minus 1 over H2 times, so in other words, it's e to an integral of H1 over H2 divided by minus H2. So in other words, rho is this expression here times L1, and it's that on L0. So in other words, what you do is you take the original differential equation. After you've divided by H2, you get this, and then you multiply it by this thing here, which we call rho. And so rho is then this exponential divided by minus H2. And this thing then becomes the P of the differential equation. So in other words, this is what we call little p. It's the thing that's in between the d by the two d by dx's. All right, so that's just a little bit of algebra and calculus that shows you can take any second order differential operator and make it formally self-adjoint. Now, it's formally because we don't know about boundary conditions, we don't know about solutions and so forth, but just looking at a differential operator and what the form of the differential operator is, we can make it formally self-adjoint. In other words, we can write it like this on the left-hand side. And then if we have an equation, LU, if L0 U is equal to lambda U, then what happens? Well, you multiply, this is really just rho L0, isn't it? And so, in fact, L on U is rho L0 on U, that's rho lambda U. So if U satisfies this equation, then LU satisfies that equation. The difference is that you have the same eigenvalue, but you regard the eigenvalue as the eigenvalue is this thing here, which is not the thing that multiplies U, but the thing that multiplies rho U. That's if you want the eigenvalue here to be the same as the eigenvalue of the original differential operator. And that's what we normally do. So what about the Wronskian of a self-adjoint operator? Well, if we start out with an arbitrary differential equation, we know the Wronskian can be written in this way. If y1 and y2 are two solutions of the differential equation, then their Wronskian can be written this way in terms of p. And so we can convert this ODE into its formally self-adjoint form. What we have is that we want to integrate this. We basically have this exponential of the integral of p of x prime, and p of x prime is little p prime over p. And so in other words, this is the differential equation. If we write it in this form, we see p is p prime over p. And so this is this integral of p prime over p. Well, this is a very simple integral because p prime over p, in other words, let me switch maybe to blue. exp of minus the integral up to x of p prime over p dx prime. Well, this is exp of minus the integral of log p prime dx prime. And so this is exp of minus log p of x minus a constant. And so this is 1 over p of x and some other constant d. And so that's how it is that this turns into this or that or that. And now we learned before, back in a few days ago, that if we have one solution to an ODE, we can find another solution that's linearly independent by integrating the Wronskian. The lower limit's arbitrary because it's an overall multiple of y1, and we're not interested in y1. We want something that's linear. We're interested in what's linearly independent of y1. And ordinarily, this would be an iterated integral because w itself would be an integral. But if the ODE is formally self-adjoint, then we have a formula for the Wronskian, namely, it's just 1 over p. And so this expression here, which is y, the second solution being the first solution times an integral of the Wronskian over the square of the first solution, it now is just an integral over the square of the first solution multiplied by the known function p of x prime, p being this p, the p that occurs in the self-adjoint form. So that's why self-adjoint form, one of the many reasons why self-adjoint form is nice. But of course, you know, it's universal because we just saw we could take any second order differential equation, make it formally self-adjoint. And so then the second solution formula is very simple. It's a constant times the first solution times an integral from an arbitrary initial point, 1 over p of x prime y1 of x prime squared. So that's a much simpler formula than the general formula. And for example, Legendre's differential equation, there's a solution for the y of x just equal to 1. It gives you a solution of this differential equation, and p is 1 minus x. So the second solution corresponding to the trivial solution is 1 over p, just 1 over p integrated, p being this, and that gives you a log of 1 plus x over 1 minus x. This is singular at both ends, So it doesn't satisfy Dirichlet or Neumann boundary conditions. That's why when we talk about Legendre's equation, we look at the Legendre polynomial solutions as opposed to these guys that don't satisfy the boundary conditions. Now, in quantum mechanics class, we talk about P as being Hermitian. We say that P is H bar over I d by dx, and we say this is Hermitian. And I thought I would show you why it is that P is Hermitian. And so in other words, let's consider a first order differential operator and ask that it be self-adjoint. So how do you take a first order differential operator and decide and make it self-adjoint, or find out if it is self-adjoint? Well, what would we want? What we would want would be chi star L psi to be L dagger chi star psi or L chi star psi. So we start out with H1 derivative H0, we have chi star times this expression here. Then we integrate by parts. And then we integrate by parts again. And when we've integrated by parts twice, if we assume that the boundary terms vanish, and in order to get this to work, we want this to be an L here. Because we've got here L psi, we want this to be L chi. So we've got a star, but this has to be L chi. So this is going to be L chi if H1 star is minus H1 and if H0 star is minus H1 star prime is H0. Then this will be equal to that, which is L chi star on psi. So L will be self-adjoint if it's of this form, in which R and S are arbitrary real functions. So it's an I times a derivative times an arbitrary function, S an arbitrary function, I over 2 times the derivative of this function here. And so we see that this is satisfied by the momentum operator. Here we have R is equal to minus H bar. It's a constant, so its derivative is 0. And we have S equals 0. So this is formally self-adjoint. And then the boundary terms are 0 if the functions vanish at A and B, which often are taken as plus or minus infinity. And so you basically, if the thing is square integrable, you've got to have them vanishing out there. So that's how that works. The angular momentum operator, of course, is of the form Li is epsilon I j k summed over j and k. In other words, L is equal to x hat or x cross p. Jesus Christ. X cross p. I don't want to write x. So in other words, what I really mean here is x cross p, but now the two x's are sort of confusing. So what mathematicians do is they use a hat to mean, or a caret symbol to mean cross. P is minus I d by dk, and so you might say, well, there's a problem here because you'd have P differentiating the X, but no, this is totally anti-symmetric. So J and K are never the same. And so this satisfies so the angular momentum operator satisfies this condition. The momentum in a magnetic field also satisfies this condition. So this is also self-adjoint. And this actually, just to tell you something that, again, often people don't tell you when they're teaching quantum mechanics, this thing actually represents the kinetic momentum of the particle. So it's h bar over I grad minus EA is the kinetic momentum. So now let's think about finding functions that maximize or minimize the energy functional, but subject to conditions. And one condition would be that the function be normalizable. And so let's find the minima and maxima of this subject to the condition that the norm equal 1. Well, then what we do, since we have two conditions here, we use the Lagrange multiplier method. Remember what this should flash. Yeah, there it goes. Well, it's the Lagrange multiplier technique. And so we just take the two things that we want to vanish and we add them together with an arbitrary constant here. And we say, well, we're going to make this is going to be 0 when we subject to variations of u and lambda. The variation with respect to lambda equation is derivative with respect to lambda just gives us back this condition. And the other one, so now we say, let's say the variation of script E is, or curly capital E, is then this, where we're varying u not only here, but also in the Lagrange multiplier term. And if we do that and integrate by parts twice, so you've got to go through this yourselves and chug through that you've done the integration by parts properly and you get this. So if this Lagrange term is to be stationary with respect to all tiny changes, then U has to satisfy both the differential equation and the boundary condition. These are the so-called natural boundary conditions, which are the ones involving derivatives at the endpoints. And actually, I forget whether these are Neumann or, let's see, which are they? Dirichlet is 305. Oh, Christ. All right, never. It's either Dirichlet or normal. Anyway, it's the ones with derivatives. That's the problem of using names. That it's you have to remember what the name means. Or if you say it has to satisfy not only the differential equation, but also the boundary conditions with derivatives. So then, in other words, if we're satisfied, if we are looking for functions that render that minimize or maximize the energy with respect to changes of the functional, minimize, maximize the energy, and are normalized, then they have to satisfy both of these conditions. And in this case, the function that minimizes the energy subject to the normalization condition is an eigenfunction of this self-adjoint operator. In other words, it does this and with eigenvalue lambda. And so it has this form here. Now, what is lambda? How is lambda related to other things? Well, it turns out lambda is the ratio of E to N. And in order to see that, what do? Well, so let's see. So we take lambda, here's the normalization integral, multiply it by lambda. We say we have a solution of the differential equation, so we can integrate by parts twice, and lo and behold, we get E. So E and N, and this tells us that lambda is the ratio of E to N. And in fact, not only is lambda the ratio, but the eigenfunction u is the eigenfunction that minimizes this ratio subject to the boundary conditions. And to see that, we then vary u. We ask for the variation of r to be 0 when we vary u, and we get variation of e over n minus e over n squared variation of n. But we multiply both sides by n, so we get this equation. And then that equation is that just that the variation of e is the variation of n times r. And on the other hand, what's the variation of e? That's this. What's the variation of n? It's that. And so we find that the function that minimizes the ratio satisfies this differential equation, and the eigenvalue is this r. So the bottom line here is that if you have one of these self-adjoint systems, so let's go back to here. If you have a self-adjoint system like this, then the functions that minimize the energy subject to the boundary condition are those that satisfy the Sturm-Liouville equation. Where is that? All right, I've gone way off the page. The Sturm-Liouville equation like this. And the eigenvalue is the thing that minimizes the ratio of e to n. And okay, well, I think we've done enough about that. But you should read that over and understand it, because it's very important from the point of very important in understanding quantum mechanics, or it's the mathematical basis for quantum mechanics. An example is the infinite square well. We've got I dropped my pen, so what we've got here is let us say we have a potential that looks like this, and it's V here, infinite otherwise. So if we draw the axes like this, and this distance here is V, that's V. And on the other hand, V is the potential is infinite outside of that. And so if we have here, let me switch to, let us say blue, we have here A and B. Well, unfortunately, well, anyway, we have A and B. A is negative in this case. And the potential is infinite for X less than A greater than B. And the mean value or average value of the Hamiltonian is this energy functional integrated effectively from A to B, because we're going to have the function vanish outside that region. And so the energy functional then is this, and it's subject to the constraint that integrated from A to B, it's equal to 1. And so then it's, if you vary this subject to this boundary condition, you get this equation here, where the eigenvalue you see is the Lagrange multiplier. I should have said that more often. So then we want to satisfy this differential equation Well, the solutions are the u's can just be sines of a constant times x. The lambdas then are the square of that constant plus v being a constant in this case. And these are all the eigenfunctions actually, and all the eigenvalues. And well, we're basically out of time. I think we'll come back tomorrow, and I'll just work on this example and the harmonic oscillator, and something about Bessel system next time, and we'll do a little bit of this next time. Remember, this is for those of you new to UNM. This week is fall break. We have class tomorrow at 5:30, but no class on Thursday. So Thursday's a holiday. The homework due next Monday has been posted. Oh, and one thing that I forgot to mention. I've been holding office hours by sitting on a chair in the courtyard of Pais, but I've done that, I don't know, 5, 6, 7 times. Nobody's come. Well, one person came once, maybe one person came twice. I don't really remember at this point. Anyway, it's gotten cold, and I think it's more effective for me to Zoom. So here's what I'm going to do. On Mondays from 3 to 5, I'm going to open Zoom and let you all log into Zoom if you want to. And I'm not going to record anything. And instead, if you want to ask a question, you can just talk, and you can write in the chat chat window, and you can talk and ask your question, and I can try to answer it. Several of you can be on at the same time. And as I said, no recording. And remember, every question is legitimate. There's no such thing as an illegitimate question. And I will not regard any question as stupid. The only stupid question is the no question. That is to say, if you don't ask any questions at all, that's kind of stupid, because then you're not going to learn anything extra, unless, you know, the guy next to you is asking a lot of questions. So to repeat, Mondays, office hours, 3 to 5 via Zoom, no recording. And so you've got to be there and ask questions if you want to learn anything. And because there's not going to be anything on Zoom, on YouTube for you to look up when the next day. All right, I'm going to stop. I'm going to stop recording now. There.